In earlier lessons, you have studied the theory of perfect competition. This theory makes a number of strong predictions about markets. For example, it predicts that the price we observe will equal both the marginal cost of producers and the marginal utility of consumers. The theory also predicts that the quantity traded in the market will equal the quantity supplied by producers and the quantity demanded by consumers. Do real markets behave as the theory suggests? We cannot just assume so. After all, the theory makes a number of abstractions which are just not true of the real world. Most obviously, the theory assumes price-taking behavior by consumers and by producers, while in the real markets that we see in the real world, at least some agents set the price at which they are willing to buy or sell. Usually, the seller names a price. Buyers may accept the price, offer a lower price, or shop around for a seller which will himself offer a lower price. Other sellers may jump in with lower offers than the first. So the theory of perfect competition has abstracted from all the details of price formation in real markets. Does this mean that the theory you have studied is wrong? Not at all. It is quite possible that the theory does a good job of predicting the price and output found in markets, even if it doesn't accurately describe the process of market trading. We can discover whether this is so by testing the theory in a controlled setting. These students are participating in a laboratory experiment. They are buyers and sellers in a market. The market is not for a specific commodity like beer or pizza, but for an abstract commodity called a token. Each buyer in the market has a redemption form like this one. This buyer's form tells her that the first unit she buys is worth 93 lab dollars. You can think of this as the marginal utility of the first token she buys. Lab dollars are converted to real dollars at the end of the session. In this session, 100 lab dollars would be converted into 7.5 Canadian dollars. Notice that the redemption value of the second token is only 37. If the buyer purchases a second token in this round of the experiment, she will be able to redeem it for 37 lab dollars, in addition to the 93 lab dollars that she gets for the first token. The redemption value schedule induces a demand curve for tokens. Here is the buyer's individual demand curve. The height of each bar shows the redemption value of the corresponding token. The horizontal line shows a price of 80. The redemption value of the first token is greater than 80. Therefore, this buyer should be willing to buy at least one token. The redemption value of the second token is below 80. Therefore, this buyer should not be willing to buy a second token. Therefore, her quantity demanded is 1. In this experimental session, there are 4 purchasers, traders 1, 3, 5, and 7. Each has a demand curve, like the one you just saw. When we put these demand curves together, we get a market demand curve. In this picture, we can see the willingness to pay for each buyer. Trader 1 has the highest willingness to pay, 93. Then comes Trader 3 with 85. Next comes Trader 5 with a willingness to pay of 77, and so on. Again, the horizontal line shows a price of 80. If sellers are asking 80 for tokens, traders 1 and 3 will make a profit by buying 1 token each, but traders 5 and 7 would lose money if they bought any units, since their redemption values are all below 80. This subject is a seller. He has a cost form like this one. The cost form tells the seller the cost of each token he supplies. For this seller, the first token costs 9 lab dollars. You can think of this as his marginal cost. Suppose the seller sells one token for 50 lab dollars. Then he has made a profit of 50 lab dollars of revenue minus the 9 lab dollars of cost for a total profit of $41. Notice that the marginal cost of the second token is 29. If the seller sells the token for $45, he will make a profit of 45 minus 29, or 16 lab dollars on the sale of the second token. This is over and above the profit made on the first sale. In this experiment, there are 4 sellers. Each of them has a marginal cost schedule, like the one you just saw. If we put them together, we get a market supply curve. Just as before, we can mark in the individual sellers corresponding to each step on the schedule. This picture shows the market supply curve. The theory of perfect competition predicts that the market price and the quantity traded will be determined by the intersection of supply and demand curves. This picture shows the supply and demand curves on the same diagram. The schedules cross at a quantity of 8 units. At any price between 33 and 37, both the quantity demanded and the quantity supplied will be 8. So the theory of perfect competition predicts a price anywhere in this range. Will the theory work? Let's look and see.
4 asks 50.
4 asks 50. 8.
8 asks 35.
8 asks 35. 1.
1 bids 20.
1 bids 20. 5.
22.
5 bids 22. 2.
2 asks 30.
2 asks 30. 7.
It's 25.
7 bids 25. 4.
Accept.
No, 2 accepts. 7 at 25. Next unit.
This token was purchased by trader number 7. After recording the transaction, his record sheet looks like this. The buyer entered what he paid for the token and calculated his profit. The token was sold by trader 2. After recording the transaction, her record sheet looks like this. Now the auctioneer opens trading for another unit.
25. Next unit. 3.
3 bids 25.
3 bids 25.
4 asks 50.
4 asks 50. 5.
26.
5 bids 26. 2.
2 asks 40.
2 asks 40. 1.
1 bids 27.
1 bids 27. 4.
4 asks 35.
4 asks 35. 5.
28.
5 bids 28. 7.
It's 30.
7 bids 30. 6.
6 bids 34.
6 asks 34. 4.
4 asks 33.
4 asks 33. 5.
Accept.
5 accepts 4 at 33.
Back in the office, the experimenter can examine the results of the experiment. This graph shows the result of a double auction market like the one you have just seen. In this market, the first unit traded for a price of 63, well above the competitive equilibrium band. The next one sold for 69, even more. But the third, fourth, and fifth prices were below the equilibrium band. The sixth trade was at 33, on the lower boundary of the band. The last trade of the period was well above the competitive level. How did the theory do? Not very well, you might say. 6 of 8 prices were outside the predicted range, and the quantity was 1 short of the quantity predicted. But that was just the first period. Let's look at the second period. It was just as bad. With 7 trades, and only one competitive price. But in the third period, there are 3 prices in the competitive range. And in the fourth period, 8 units are traded, and 5 prices are in the competitive range. Here are the prices for the rest of the session. They were either right in the competitive range or just a little way outside of it. In all of these cases, exactly 8 units were traded. So by the fourth time period, buyers and sellers have discovered the competitive equilibrium price and quantity. They did this without knowing each other's supply schedules and demand schedules, and without solving any equations. The market process by itself led to competitive equilibrium. This finding, that prices and quantities traded in double auctions rapidly converged to competitive levels, has been replicated in the laboratory many times. It represents a real victory for the theory of perfect competition. It shows that the predictions of the theory can hold, even in a market in which buyers and sellers announce prices rather than taking them as given, and with as few as 4 agents on each side of the market. In addition to testing economic theories, laboratory experiments in economics have discovered new facts. One of the most important discoveries is that market institutions influence market outcomes. A market institution is a set of rules governing the interaction of buyers and sellers. In the experiment we just saw, the market institution was an oral double auction. In a double auction market, buyers and sellers are both allowed to make and to accept offers to buy and sell. To prevent confusion, offers to buy are usually called bids, and offers to sell are often called asks. There are many other market institutions. For example, many retail markets are posted offer markets. A posted offer market is a market institution in which one set of agents, either buyers or sellers, submit binding offers to trade, and the remaining agents choose which offers to accept. Retail markets, strictly speaking, are posted ask markets because it is the sellers who announce their asking price and buyers who do not generally haggle with the individual seller. Instead, buyers usually search around to find the seller that is willing to sell the goods that they want at the lowest price. Laboratory experiments have shown that prices in posted ask markets tend to be above the level predicted by the theory of perfect competition. Let's look more closely at a posted offer market. In an oral posted ask experiment, sellers fill in a form announcing the price they will ask for tokens. They must also decide how many tokens they are willing to sell at that price. Usually they will try to sell all the tokens with a marginal cost less than the posted price. The offers are written up on the chalkboard, and each buyer, in random order, is allowed to choose to purchase as many tokens as he or she wishes from whichever seller she chooses. Let's look at the results of a posted ask experiment. In this session, there were 4 buyers and 4 sellers. The redemption value and marginal cost schedules were the same as in the double auction session that we looked at earlier. The only difference is that the market institution has changed. In the first period of this session, Trader 2 posted a price of 10. Traders 4 and 6 posted a price of 15, and trader 8 posted a price of 49. Trader 2 sold his 1 unit at 10, but the marginal cost of his second unit was 35, so he could not sell it. Traders 4 and 6 also sold 1 unit each at their posted price of 15. But trader 8 sold both of his units at a price of 49. In the second period, things changed. Trader 6 posted a price of 50 and sold 3 units. Trader 8 posted a price of 52 and sold 2 units. Traders 2 and 4 posted very high prices and sold nothing. All the trades were above the competitive equilibrium band of 33 to 37. Similar results prevailed in periods 3 and 4. Indeed, throughout the session, prices remained substantially above the competitive equilibrium price. This result has been replicated many times in the laboratory. Posted ask prices tend to exceed the competitive levels. Similarly, posted bid prices tend to be below competitive levels. This shows us that market institutions matter. If market institutions lead to different outcomes, can we say which one is best? The answer, of course, depends on what you are trying to achieve. Economists frequently adopt efficiency as a criterion for evaluating the outcome of markets. A market is efficient when all possible gains from trade have been achieved. Consider the demand and supply curves that were induced for these experiments. If trader 2 sells his first unit to trader 1, trader 1 gains a token worth 93 to him, while trader 2 gives up a token that cost her 5 to produce. The net gain is 93 lab dollars minus 5 lab dollars, or $88 in all. This is shown in red in this picture. The net gain is the sum of the buyer's profit and the seller's profit. The price of the token determines who gets the largest share of these gains. If the price is high, the seller gets most of the gain, while if the price is low, the buyer gets most of the gain. In the context of these experiments, efficiency is the same as maximizing the total profit of the buyers and the sellers in the session. This makes it easy to define an efficiency index. The efficiency index is computed by dividing total actual profit by the total achievable profit and expressing the result as a percentage. For example, to calculate the efficiency of the first period of the double auction market, we divide the total profits of 312 by the total potential profits of 368 and express the result as 85%. The efficiency of the first posted price market was 67%. From the graph, we can see that the efficiency of the posted offer market in period 1 is in fact lower than the efficiency of the double auction market in period 1. This pattern continues throughout the experiment. The efficiency of the double auction market was higher than the efficiency of the posted offer market. This finding has been often replicated in the laboratory. Let's summarize what we have learned in this lecture. First of all, we have learned that economic theories can be tested in the laboratory. Secondly, we have learned that market institutions affect market outcomes. Prices in double auctions tend to equal competitive levels, and that prices in posted ask markets tend to exceed competitive levels. And finally, we have learned that double auction markets tend to be more efficient than posted offer markets. Auction markets tend to be more efficient than posted offer markets.